Hello and welcome to our 14th video. My name is Yaman. This video will be about the anti-chain rule derivative. The name may sound weird, but hopefully it will not be at the end of this video. So enjoy it. Let's go ahead and start with our hypothesis. We say for any function y equal to f of x, the anti-chain rule derivative, which is represented by integration of y multiplied by its derivative y prime dx, can be performed by, and we're going to go ahead and just expand y prime to dy by dx. So instead of integration of y multiplied by y prime dx, we're going to go ahead and use integration of y multiplied by dy by dx. Now we have dx in the numerator and dx in the denominator. We could just cancel these two and we will end up having integration of y dy, and we call that a theorem for now, for the lack of a better word. I don't know if it deserves to be called a theorem or not, but let's say theorem is integration of y dot y prime dx equal to integration of y dy. Integration of y dy, y to the power 1, we'll just raise the power by 1, it becomes y squared, and then we divide by the new power, which is y squared over 2 plus constant. So this is pretty much the theorem that we're talking about, where this is just like the chain rule. So integration of the chain rule is equal to integration of just a function with respect to itself. And that's what we'll be doing. And let's go ahead and take an example. So our example, we said use the theorem to find integration of cosine x sine x dx. So we know that cosine x and cosine x are related because sine x is a derivative of cosine x, so we can apply this theorem. So we'll go ahead and let y be equal to cosine x. So we'll use y equal to cosine x, and that will lead us to y prime equal to negative sine x. And negative sine x is equal to negative the derivative of cosine x. Let's go ahead and plug in the values. So for integration of cosine x multiplied by sine x dx will be equal to, and we have a negative sign. I'm going to talk about it in a minute, but we have cosine x as it is, but then instead of sine x, we replace sine x by its value. So the value is d by dx of cosine x. Now, why did we put this negative sign outside? For the simple reason, d by dx of cosine x will give us negative sine x. So if we put negative sine x here, and we didn't have negative before the integral, then we're having two different values. Over here we have all positive values. Over here we'll have cosine with positive value, but sine with negative value. That's why we have the negative outside. That's why we had minus sine x equal to minus derivative of cosine x. It sounds like if we did derivative of cosine x, we'll get negative. So negative by negative will be positive, and then this positive is not equal to this negative. No, it doesn't work that way. But anyway, I hope it is clear now. Let me just repeat it. We said we need this negative outside here because if we did the derivative of cosine x, it's going to produce negative sine x. And we need the negative outside to make sure that we have the integration of cosine x multiplied by sine x. Having said so, let's go ahead and also proceed. So we have dx in the numerator and denominator. We could just cancel the dx's, and we'll end up with integration, negative integration of cosine x, and then over here, instead of going through all these cancelled out, we just write down d cosine x. And now it makes sense to just use the theorem because we have a function and then d the derivative of the function, and all we got to do is just do the mapping. We put y equal to cosine x, so d, and then of this y, instead of that y, we'll also put cosine x. So cosine x d cosine x, y dy. For y dy, the integration is y squared over 2, so why not for cosine d cosine, the integration of cosine squared over 2? But we're preserving the negative sign because we have the negative sign before the integration. So the answer will be negative cosine square x divided by 2 plus constant. Let's go ahead and try to do the same, but we take y equal to sine x instead of cosine x. If we take y equal to sine x, then what we will have is we will have y equal to sine x, then y prime equal to cosine x. And we're going to go ahead and say cosine x equal to derivative of sine x. Now we'll go ahead and do the plugging. So we have integration of sine x cosine x dx equal to integration of sine x, but instead of cosine x we take the equivalent, which is d sine x by dx. Once again we have dx in numerator and denominator. Let's get rid of them, and then that will leave us with integration of sine x d sine x. So integration of sine x d sine x, in a similar manner we could just say that we're mapping. So integration of y dy is equal to y squared over 2 plus constant. So integration of sine d sine should be equal to sine squared divided by 2 plus constant. Now that we have gone through the integration and we got the results for two cases, a case where we used y equal to cosine x and a case where we used y equal to sine x, and we have the results for both cases, but I'm sure that these results are correct, but I have to prove it. To prove it, we're going to use the fundamental theorem of calculus, because these are integrals. If we did the derivatives of integrals, we have to get back to the original function, which is cosine x sine x. If we didn't, then the theorem is wrong. So let's go ahead and try to verify these two examples. To verify the examples, we're going to go ahead and apply the fundamental theorem of calculus. Like I said, we compute the derivative of the integrals 2 and 3, just to confirm that it worked for all cases, because this is just without loss of generality. So let's go ahead and use the chain rule in the process. So if we have derivative of y squared by dx, we will just say it's equal to twice y and then multiply it by y prime. That is the derivative of y squared and then the derivative of y. Derivative of y squared is 2y. Derivative of y is y prime. So we're going to go ahead and use this one handy. Now, our first result was negative cosine square x divided by 2. So we want to go ahead and do the derivative. If we did the derivative and the derivative annulled the impact of the integration, then we'll get back to sine x multiplied by cosine x. Let's see if that's going to happen. We said we're going to use the chain rule. So cosine square, derivative of it will be derivative of cosine square, which will give us 2 cosine, and then derivative of cosine, which will give us negative sine, and that's what we want. So this is the derivative. Derivative of cosine square will give us 2 cosine, and we're preserving the negative. And then derivative of cosine will give us negative sine. So we have negative, the negative are gone, and then the 2 in the numerator and denominator, we can cancel them, and that will give us what we need, which is cosine x sine x. This verifies the case when we used y equal to cosine x. Let's go ahead and take a look at the second case when we used y equal to sine x. So we're going to go ahead and do the derivative of this integral. This is the integration of the same function. Integration of the function sine x multiplied by cosine x. So if we did the derivative of this and it resulted in sine x cosine x, that means the derivative annulled the integration and satisfied this fundamental theorem of calculus. That means our result is correct and our theorem is valid. So let's go ahead and do the derivative using the rule. So derivative of sine squared x is 2 sine x, and then derivative of sine x is cosine x, and that's what we will get. 2 sine x cosine x, but this divided by 2, so the 2 cancels the 2 and we get the result. So we're back to the same function, so everything is valid. Let's go ahead and give another example. Let's suppose that we want to look at the integral of tan x sec square x dx. First, we have to prove that this is the derivative of the first. So we have to prove that sec square x is the derivative of tan x. To do so, we'll just go ahead and differentiate the tan x. So differentiate tan x is similar as differentiating sine x over cosine x, and for this one we use the integration of the ratio. So what we have over here is the quotient, and if we use the quotient rule, then we will have the denominator square and then cosine square x plus sine square x, where the first one is the denominator multiplied by the derivative of the numerator plus the numerator multiplied by the derivative of the denominator, and the plus is coming because of the cosine derivative is equal to 1, but normally it should be negative. Anyway, this is the chain rule. So we know that cosine square x plus sine square x is equal to 1, and that will lead us to 1 over cosine square x, but the reciprocal of that will be sec square x. So now we prove that the derivative of tan x is equal to sec square x. That means this is valid now and we can use our theorem. So since we proved that the derivative of tan x is sec square x, we could go ahead and proceed with the anti-chain rule derivative, and we will do it as follows. So we let y equal to tan x, then y prime equal to sec square x, which will also represented by d tan x by dx. And if we did the plugging, then we will have from our theorem integration of tan x sec x square dx equal to integration of tan x, instead of sec square x we put derivative of tan x dx. And now that we have this dx in the numerator and denominator, we can cancel them and we will end up with integration of tan x d tan x. And we know from the previous examples, anytime we have the d hugged between the same functions, tan x hugging the d, and we have integration, then we will just go ahead and get the answer, which is tan square x divided by 2 plus constant. And that proves our theorem. Thank you for watching this video, and you have a great day, and we hope that you will subscribe our channel. You will have more interesting subjects coming. Thank you, and you have a good day.